Good afternoon. So this is session 2 of sweep frequency response analysis. So we're going to talk a little more about the actual sweep frequency response. We're going to talk a little more about actually how we're going to go about doing this response and a little bit about analyzing the response. So first of all, we want to take a quick review back into capacitance. Now we've studied capacitance and inductance both, uh, but we've studied them some length ago and in a different class. So we're going to start looking at it with respect to what's going on in a sweep frequency response setting. So when you look at the sweep frequency response with respect to capacitance and inductance, we need to understand what goes behind capacitance. So the farads, the capacitance, this is in farads of a capacitor, is a function of the area of the surface. Remember, I told you before, back when I was in school, we made capacitors out of aluminum foil and put pieces of paper in them. So the area of the surface that's actually going to hold the charge is one function. The distance between the two plates, the small d here, and then we have some constant, and that's the dielectric constant for the material that we have in between the two plates. So we'll review that on the next slide. So if I look at this capacitance here, and let's just say this capacitor, the first one shown here under letter A, is 5 microfarads, because I have some area A here and some distance here. If I increase the area by 3 times, but I keep the distance between the two plates the same, then I've increased the capacitance by 3 times. It's now 15 microfarads. Now, for item number 2, I've got capacitance is 0.1 microfarad, and I kept the area the same. Area here is equal to the area here, but I've increased the distance between the two plates, and it's twice the distance. So it's 1/2. So the new capacitance would be 0.05 microfarads. And that's simply by changing the distance between the two plates. And here, the third thing is I can actually change the material between the two plates and change from air maybe here to now a paraffin paper, and I got 2.5 times the capacitance. Well, guess what? I'm not going to change the material between the two plates. And I don't think I'm going to change the area of the plate itself, because it's the actual copper winding in the transformer that I'm looking at, and the winding being in close proximity to the next winding. But what does happen is those windings can shift for a multitude of reasons. There's blocking between each winding. If one of those blocks shakes out because of vibration or through fault, or if there's displacement in that winding, then one between two windings, the distance may increase, but between the other two windings, it might decrease. In either way, I'm going to have a change in the total capacitance between those two windings. So I'm going to have a sensitive device, a sensitive instrument, which is my sweep frequency response analysis, that's going to review this, and it's going to be able to monitor even for extremely small changes in capacitance. And that's what we're going to be looking for. Now, if we look at the actual transformer here, we have transformers that when you have faults, the stresses are just unbelievable. Faults, overloads, or surges, but faults, they're unbelievable. So if I can see the forces here where the actual winding would go out or go in, that's called buckling, okay? I can see axial forces here where windings would want to shift down or shift up. Here's a case where you can actually see some of those shifts right in through here. So those stresses can cause physical damage. Now I have lots of little plates in here, little blocks of wood or special paper that are in there that are actually holding these windings at certain locations. If during one of these faults, the forces inside are so strong that one of those blocks moves, then I will actually change the capacitance between the windings. So that's what we're looking for. Uh, Allowing a transformer to enter back into service without catching these types of problems is risky, can be very catastrophic. And I want you to know that a lot of these problems may not be caught with our typical test that we run. Turns ratio, the turns may be perfect. Winding resistance, the copper's still there, may be perfect. Excitation might change a little bit. Power factor may stay the same because I haven't had any insulation problems. So this is just another tool in our toolbox to be able to assist us in trying to determine if there is a change. Uh, so we'll talk about when is best to actually do the test here. But if we're going to look at it, this sweep frequency response analysis, the SFRA, we're going to be applying a 20 volt peak to peak signal. So it's a very small voltage that we're going to apply. And we're going to change the frequency of that signal all the way from 20 hertz all the way up to 2 megahertz or 2 million hertz, okay? So we're going to sweep the frequency all the way across that, remembering that when I look at capacitors and inductors and I look at resistors, that looking at the equations, 1 over 2 pi, FC for that capacitor, 2 pi, FL for that inductor, and the resistance stays the same. As the frequency goes up, that inductance goes up, okay? And as the frequency goes up on a capacitor, the capacitance goes down. So if you start looking at a sweep and you see basically a really strong signal coming back, so your dB losses are smaller. We talked about dB last week. dB losses are smaller at the lower frequencies, then I know that at the lower frequencies that the path that that circuit is taking is through the inductor, okay, because that would be nearly 0 ohms impedance. At the high frequencies, if I see a pretty high return on my input, I know that I've got to be dealing with the capacitive portion because that's when the capacitance would be near 0, the capacitive reactance. So those are the kind of things we're going to be looking at, and we're going to be looking at those graphs. So the response measured at a second bushing terminal. Typically, it's on the same winding. So for all the tests that we're going to do, we're going to be looking at a different bushing on the same winding, okay? So then we're going to be reviewing those resistive, inductive, and capacitive components throughout that one winding that we're passing through for the apparatus. And we're going to be comparing that with previous test data. Now, the other thing that's really important to us, that at 20 volts peak to peak, we can run this test with no oil in the transformer. I've never done that, but I've heard of people that have done that. We just need to make a note of that because the results would be different with no oil than it would be with oil because, again, that dielectric between the winding would be different because there's now oil-saturated paper. So this result of the output, the 20 log base 10 V out over V in, measuring the output signal divided by the input signal, doing 20 times that log. It produces a fingerprint, okay? Now, a lot of times that's called a transfer function. We'll talk about that a little bit later, but that's like a high math thing that we don't really need to get involved with then. But we can validate the power apparatus mechanical and geometrical integrity. Look at that, mechanical and geometric integrity. We can evaluate it. As a matter of fact, I'm under the belief that used to be when the transformer was shipped from the factory, it was shipped and they put an impact recorder on the rail cars and you would see if they had had any serious impacts along the railway. And when you got to when you received a transformer, you would actually have the output of that impact recorder reviewed to make sure that something hadn't happened along the way. I don't think you even need the impact recorder anymore because if you get the sweep frequency response at the factory and then you do it after you get it set on your pad, you can tell if something's moved inside there. It's fantastic. So it'll tell you about winding distortion. It'll tell you about shorted turns. Now, other tests should be able to tell you about the shorted turns as well. It'll detect core and winding movement. Other tests won't necessarily do that. So, what can it tell? It can provide an indication of any kind of winding movement or any kind of electrical short inside that transformer, anything that's going to change any of the characteristics of that resistive inductive capacitance network. It can tell if something is damaged or broken inside that transformer without going inside. Now, I know that this is really difficult for some of our customers to understand, but we can't fix most things inside of the transformer that are broken by getting inside. Sometimes we do get inside, but we can't fix much. But the other thing is, if you've ever been inside a transformer, if you get inside there, you can't see much. So you might be able to do a thorough internal investigation of that transformer, and you still might not see anything wrong inside there, but this test will be able to tell you that there is something wrong. And with practice, you can actually get a good indication of what part of that transformer that the problem's in. Now, the other thing that's really important is historical data is super, super important. I can't stress enough that historical data on the same transformer is the best thing that we can have to review for our test. So sweep frequency response, you're going to say, why don't we do that all the time? Why isn't that the only thing we do? Because that's not the only thing that we need to do. It's just one of many tools that we have. We have that power factor and capacitance test. The capacitance test on the power factor might catch some movement in the winding, but it might not. Power factor test is going to give you a good indication of the insulation properties inside that transformer and to see if there's any deterioration or any contaminants in the paper or the oil, and it's going to tell you of any kind of concerns as far as any kind of shorting or those sorts of things. So it's an important test, but it's in addition to the sweep frequency response. Leakage reactance is the same thing. We're still always going to do our turns ratio test because that's a basic test, can be done very easy. Insulation resistance test, the sweep frequency response has nothing to do with insulation resistance test. You can have windings that are buckled horribly inside. You can have blocking material that's actually in the bottom of the tank now, and windings have bulged out, but still have a good insulation resistance test. Same thing with winding resistance. The winding resistance test is a totally different test, and it has to do more with the copper and also the electromagnetic circuit. So that we might not catch that with a problem inside. Exciting currents might catch. That'd be the closest. Dissolved gas analysis, oil screen, those are great tests, but they're not going to tell you about movement inside the transformer. The sweep frequency response is the end tool for that. So when we look at it, it's when to test and why do we actually want to test? Well, at the factory, okay? At the factory, we want benchmark tests. That's very important. Now, understand that we've got benchmark tests, but there's some things different in the factory that might look different in the field. For instance, they may put different bushings, and they may have a set of bushings at the factory floor that they put in all the transformers they make of that size. And when you get to the field, you install some different bushings, so there may be some differences there. Now, when they do a test in the factory, I'd like to have that benchmark test, but they also do a short circuit analysis test, short circuit test in the factory to determine the various components of the transformer, the impedances inside. So they do open circuit tests and short circuit tests. After that short circuit test, I want them to do a sweep frequency response as well, because that is a stressful test. And in the factory, they can also do it for quality assurance. Now, in the field, I want to follow up because I want to use the sweep frequency response as a diagnostic test after it's shipped, okay? And I'm not one that says we need to do a sweep frequency response analysis on every transformer every time we test. I think there needs to be a reason. After that transformer's been relocated, maybe it's sitting one sub for a while, maybe it was sitting in a spare yard for a while and then moved somewhere else. We've moved it. Anytime you move a transformer, there's a chance that you could have bounced it somewhere. So I want it checked then. Routine testing, again, a lot of customers want it done routinely. I'm not big on doing it routine on every transformer, every test. I'm more concerned about when they see 3 faults or high load conditions. After a transformer alarm, if you got a sudden pressure alarm, yeah, I'd really like to see an SFRA done on it, because sudden pressure means there's pressure built up inside there. What happened? Was that an internal fault? Did things bulge? After an incident, any kind of through fault, or if it's tripped offline, I think that an SFRA is a valid test to run. So it's going to find radial deformation. Okay, it's going to find that windings is telescoped. In other words, blocking's gone. It's kind of spread out, like the old slinkies that we used to have. It's going to detect turn-to-turn shorts. It will detect open circuits. But you know what? Other tests will catch that as well. Any high resistance connections, which could be the load tap changer, could be the de-energized tap changer, or any movement of components. It'll check those things for you during that test. So as a review from the last time, here's the diagram of the actual transformer and the internal components. So when I look there, I see that they're all series and resistors, inductors, and capacitors. Okay, so I've got a winding here. There's a low voltage winding I'm going to apply a voltage to with a signal, and it's going to go to the next one. And I want to put my other lead right here, the next winding. And looking at it here, here's all four layers of the winding itself. And I can see that if I inject here, what's going to happen as the frequency is low, frequency equals low, I'm going to find paths with inductors in it. That's this guy, that's this guy, that's this guy, that's this guy. Remember, resistance didn't change. As frequencies increase, I want to find out, it'll go through paths of capacitance, this way, this way, this way. So that's where we're at. And notice we got all the lower clamping section and the upper clamping channel. So we've got everything there. So we have to understand that for various frequencies, it's going to go through various paths. So let's talk a little bit about test preparation. So obviously the transformer's got to be disconnected from the system, okay? Transformer should be in normal service condition. I want it to be assembled and oil filled, because that's what I want to use for my historical data, oil filled. If it's not oil filled, make a note of it, because it's not comparable to historical data. The transformer of the tank needs to be grounded, and this needs to be a good ground. I can't stress enough the fact that you need to brush off paint. If this transformer is sitting in a storage yard, just sitting here, you got to get it to a good ground, because you're going to get some really funny readings that are just not comparable with anything if you don't have good grounds set up. So, and you're going to make up the connections for the various configurations of the windings. We'll talk about that briefly in just a second. And then the other phases that are not under test are left floating, in other words, disconnected. So we're going to go through some various points here. So let's talk about tap positions. So on the high side, or if the transformer, all I've got is the de-energized tap changer, I want to leave that tap in a normal operating position. That's where it's been. That's where it's going to be. If the customer wants to change that, again, we need to have a waiver sign saying if it breaks during the tap change, it's your problem, not ours. We didn't cause it. We typically don't like to move those de-energized tap changers. So we're gonna do that test in a normal operating position. We're gonna note that on our test sheet so that even if the tap gets changed next time, we got to refer back to it. If we have a load tap changer, which we do lots of times, we want it in the extreme position, because I want to be able to capture the entire winding, everything on the entire winding, okay? And then when we follow up, we need to make note of that, and we test it on the same position. The thing is sensitive enough on the test that if I go out there and check it at 3 rays, and then Melvin goes out a year from now and checks it on one lower, they're going to have 2 separate results, and we won't be able to compare. Test it in different tap positions will alter the response. We already talked about that. If you've had an event, if you've had a through fault, if a relay protection scheme has tripped this transformer offline, let's test it on the tap that it's on first. Review that, even though we don't have historical data to compare it to, but let's review that, and then let's go back to the tap that we normally check on. So that would be 2 tests that we'd need to run. Now, we're going to measure the frequency response, all the resistors, the inductors, the capacitors for the transformer, and we're going to plot the results. Now, those plots typically are called transfer functions. Okay, that's a good legitimate call. Back in school, we called them a Bode plot. I don't expect you to remember that, but that's what they are, frequency response. In our world, we say that that's our footprint. That's just like a fingerprint for this transformer. That's our footprint. That's our baseline. That's what we're going to go with from now on out. And everything's going to be compared to that. So the actual setup. Now, the actual software will help you make these determinations. But basically what I want you to remember is the fact that I'm going to do 3 tests that are from the high voltage bushings, high voltage windings, high voltage open circuit test. So I'm going to go from one winding to the next, one winding to the next, one winding to the next. Okay, that's going to be 3 sets. That's going to be on the delta, go winding to winding. Okay. If I've got a Y, I'm going to go winding to neutral, winding to neutral, winding to neutral. I'm still going over a winding, but just to got to understand that on a Y, I'm going to go from H1 to HO, H2 to HO, H3 to HO. So I'm actually putting this transformer configuration is a delta Y. So let's start out with the delta configuration. So I'm actually inputting a signal on H1, and I'm going to receive that signal on H3, and I'm going to monitor that and plot that. All the other windings, including XO on the secondary, are floating. So if I look at the open circuit test, there's going to be 3 open circuit tests from the high side. There's going to be 3 open circuit tests from the low side. During all open circuit tests, just like it sounds, every other winding is going to be floating. It's going to be open circuited, nothing there. Then after I run those 3 open circuit tests from the high side, 3 open circuit tests from the low side, then I'm going to go back to the high side and I'm going to run the same sort of test, but this time I'm going to go to the low side and short out the secondary. So in this case, again, I'm talking about a delta Y transformer. I'm going to run a test from H1 to H3, H2 to H3, H3 to H2. But on the secondary side, I'm going to short X1 to X2 to X3. And look here, I'm going to short back to H to X1. So I have to loop all the way through. I'm shorting one bushing to the next bushing to the next bushing, and then I'm shorting it back to the initial X1 bushing. Now, all others float, so the other high side bushing's floating, and I'm still leaving XO. The neutral on the secondary side is also going to be floating. So it's all floating there. And you may say, it's like, Alan, why do we need that return? It is so critical. Issues that you'll have with tests are the fact that you'll forget to float XO, or you won't have a great ground. It's even to the point where I want to mark on my test sheet exactly where I place my ground side of the test probe at. So it's pretty critical. And so making sure that I have that loop X1, X2, X3, X1 back is going to be vital to me. Now, so those 9 tests, 3 open circuit tests on the high side, 3 open circuit tests on the low side, and 3 short circuit tests from the high side. We don't do short circuit tests from the low side. Now this is for a simple 2-winding transformer. If you have a tertiary, we're going to be running the test differently, a lot more tests. So here's the actual connection. So this is the Doble SFRA test set. I've got ground here, and it's going to go to ground, okay? It's going to go to ground, and that has to be a good ground. And then I've got the 2 test leads here. I've got the red lead, and I've got the black lead. The red lead is actually sending the source out. The black lead is actually receiving that. So this would be V in, this would be V out. But notice I've got a ground on each one of these. So I've got a ground that's going down to the base of that bushing, and I've got a ground on this one going back to the base of that bushing. Those connections at the bushing have to be dirt free. That has to be an excellent ground connection right there at the base of the bushings. And we need to have some consistency. Don't just grab any piece up there and say, I'm going to ground. That'll make a difference in my plot. So each measurement that we make is going to be referenced back to that ground plane. So here we go. I've got VN. I've got a 50 ohm coax reference measurement lead. It's the lead that we bought with the test set. You can't use just any lead. We don't make modifications to it. And then we have this measurement lead over here. It's over here. So this is my reference input. This is my transformer, the impedance inside that I'm actually going to be reading across. So again, with definitions, open circuit tests. It's going to be called from now on in the industry, they just call it OC. And it's going to be HVOC or LVOC or TVOC, which is high voltage winding open circuit, low voltage winding open circuit, tertiary winding open circuit. So if you had the 3 winding transformer, you can see you're going to have 9 tests there before you do anything else. So if you've got a delta connection on the high side or the low side, either one, you test across each pair of terminals, H1, H2, everything else is floating. We already showed that on the diagram. On the Y winding, test between phase and neutral, H1 to HO, with everything else floating. So I can do that. The short circuit test is set up the same as the open circuit test, but the secondary or the tertiary winding is shorted and shorted back to itself. Remember again, X1, X2, X3 back to X1 and leave the neutral floating. Now, a couple quick diagrams here of actual tests that have been performed. So here is an open circuit test, and I'm not an expert, but I've done enough of them that I understand that this is a delta winding open circuit test. I can tell it's a delta because I have 2 of these little bumps at this frequency. So I start out at 20 hertz, down here 20 hertz, and up here I'm at 20 megahertz. So again, down in this range is where I'm highly inductive. Okay. Anytime I see a little blip here, those are resonant frequencies. Every blip is some resonance of an RLC circuit, positive and negative, every single one of those things. And I may not recognize these. The Doble people can actually read things pretty well, but they're all there. And so on this transformer, if I were to come back 5 years from now and run that same test, I would want to see those same resonances in the same exact place. Now, I might find that things might change up and down on the dBs, the plus and minus dBs. See, the beginning of this is minus 40 dB. I might see some changes up and down on the dB scale, but I should not see changes on where those resonant frequencies happen. And I can tell you this much, that this double hump right here is a typical double dip of a delta winding. And I can also tell you that when I get up to the higher frequencies, that typically is where the bushings are. So I'm actually looking at the bushings and the connections inside the transformer to the bushings, actually to the winding. So that would be an open circuit test. Now, what I would want to do, and I'll show you the final slide here for today's class, is we'll show you a series of slides that were taken on a test. So again, I've got a transformer here that's delta Y. I can tell by looking at it that this is the delta winding. And I can see that because of the double dip. Down here, double resonant frequencies. This one, that's pretty typical of a delta winding, very typical of a delta winding. And if you'll notice, up on the top left, it tells me the colors. So the colors were green and turquoise and a red there. So if I see the green, I don't see the turquoise and the red. Well, the turquoise and the red have mixed together because those lines are exactly on top of each other, and so it kind of looks like brown. So I've got 2 windings that are exactly on top of each other. I can see a little bit of separation right there, but 2 windings are basically on top of each other, but I see a 3rd winding that's different. So your first instinct is just like, wow, that's a problem. Well, it's not really a problem because you're going to have differences between one winding because one of the windings is on the center core and the other two are on the outside. That center core is going to have a little different response characteristic. So it's not uncommon to see in this area some variance there. And you're actually going to see it along the way here as well. If I look up at the next set of slides right here, that's my Y. That's my open circuit test from the low side. That's the Y connected side. That's these three colors, a darker blue and looks like a gold and a brown. Again, the same sort of thing, but notice I got a Y configuration. I only see the one dip there instead of the two like I saw for the Delta. But again, I see two traces basically right on top of each other. I see a little separation of the darker blue there, but basically they're on top of each other. But that middle winding is a little bit off, but the resonant frequency is pretty close on those. And then finally, the third set of tests that we have here are the short circuit tests. So I'm going back and looking from the high side, but I've shorted the secondary windings out. And I can see some traces here. And I can't tell you right now everything is happening over here, but I know that when I'm looking like from 200 hertz up to about a kilohertz, what I'm looking for that short circuit test is I want to see those lines right on top of each other. I don't want to see variances in between that. As a matter of fact, I will actually use the software to expand that section of the graph so I can see if there are any detections between there. If there's deflections that are different, even more than a couple dB, that's a concern for a shorted circuit test. Well, that's what we've got for you today. If you have any questions, you give me a call, and I'll be able to respond to your calls or your texts or your emails. I will be sending out another lesson next week. As always, I want you to respond to me on your emails. Let me know that you actually did listen to this class. So thanks, and we'll talk to you next week.